Control of raw material weigh involves precise measurement to meet specific specifications before storage. Approved raw materials are segregated and stored, ensuring accessibility and adherence to quality standards. Sand and aggregate undergo thorough washing to eliminate impurities, dust and debris, ensuring cleanliness and optimal quality for mixing. Clean sand and aggregate are prepared for precise mixing with cement. Cement, sand, and aggregate are combined for precise, high-strength concrete. Steel PC bars are cut, shaped, and prepared to specified dimensions. Steel bars are precisely cut to desired lengths and dimensions. Processed steel bars are shaped into buds for assembly. A crane efficiently transports processed steel bars to designated assembly areas for further processing. Steel bars are welded together to form sturdy reinforcement cages. Flanges are strategically attached to reinforce connection points on cages. Molds are cleaned, then coated with oils for easier demolding and to prevent concrete adhesion in subsequent processes. Once assembled, the reinforcement cage is carefully positioned and aligned within the prepared mold. Precision is crucial to ensure the cage fits snugly without displacements. This step demands meticulous handling to prevent any damage to the cage or the mold, ensuring accuracy in the final concrete pile structure. Concrete precisely mixed is poured into the mold, encasing the reinforced cage for structural formation. Precise concrete pouring encapsulates the reinforcement cage within the prepared mold. Erecting molds involves setting up the filled molds in position for curing. Proper alignment and securing ensure the concrete sets uniformly, adhering to structural specifications and design requirements. Machines apply precise tension to embedded steel, enhancing concrete strength by inducing compression, crucial for structural stability and durability. Centrifugal spinning compactly forms concrete and removes excess moisture efficiently. Excess sludge is carefully extracted to maintain concrete quality standards. Concrete piles undergo controlled steam curing for optimal strength development. Demolding involves delicately removing the cured concrete pile from the mold to avoid any structural damage. Careful handling ensures the integrity of the finished product. Once demolded, the mold undergoes cleaning to remove any residual concrete or debris, preparing it for the next casting cycle. This thorough cleaning process ensures the molds are in pristine condition, ready to create high-quality concrete piles for subsequent production runs.
The process begins with the creation of tilt-up formwork, which serves as the mold for the inclined walls. This formwork is typically made from sturdy materials such as wood, steel, or fiberglass. Steel reinforcement is a crucial component in constructing sturdy and durable inclined walls. Steel bars are strategically placed within the tilt-up formwork to reinforce the concrete structure. The wall panels are cast on a flat surface, typically the construction floor. This phase involves pouring concrete into the prepared tilt-up formwork. The The concrete is then left to cure and harden, forming the initial structure of the inclined walls. Careful attention is paid to ensure the concrete mixture meets the required specifications for strength and durability. Simultaneously, a metal structure is fabricated to support the inclined walls. This metal framework complements the concrete structure and provides additional support during the construction process. After the concrete has undergone a thorough curing process, the crucial step of lifting the wall panels from the construction floor takes place. Specialized equipment, often in the form of cranes or hydraulic lifting systems, is employed to execute the panel lifting with efficiency and safety in mind. The choice between cranes and hydraulic systems depends on the specific requirements of the project and the weight and dimensions of the wall panels. Both methods, however, share the common goal of ensuring the controlled elevation of the inclined wall panels. The utilization of cranes introduces an element of flexibility in managing varying panel sizes and weights. These heavy-duty machines are equipped with precision controls that allow operators to lift, maneuver, and position the wall panels with accuracy. The process involves attaching lifting devices securely to the panels, distributing the weight evenly to prevent any stress concentration points, which could compromise the integrity of the freshly cast concrete. Hydraulic lifting systems, on the other hand, offer a more controlled and gradual approach. These systems use hydraulic cylinders to lift the wall panels incrementally. This controlled lifting ensures that the panels are raised uniformly, minimizing the risk of deformation or stress-induced damage during elevation. Hydraulic systems provide an added layer of precision, especially in projects where nuanced adjustments are critical for achieving the desired incline and alignment of the walls. Throughout the panel lifting phase, safety measures are paramount. Construction personnel work in tandem with the lifting equipment, communicating effectively to ensure a smooth and secure operation. Rigorous checks are conducted to verify that all connections are secure and the lifting equipment is in optimal condition before the actual elevation process begins. Simultaneously with the panel lifting, the metal structure is elevated to align with the inclined walls. This integration ensures a seamless connection between the concrete panels and the supporting metal framework. The synchronization of these two components is critical to achieving a structurally sound and aesthetically pleasing result. With the inclined walls in place, the roofing system is installed using the KR18 system. This roofing system, known for its durability and versatility, complements the inclined walls, providing a comprehensive solution for the entire structure. The integration of the roofing system contributes to the overall functionality and weather resistance of the building. The final touch involves painting the inclined walls to enhance their visual appeal and protect them from environmental elements. Digging the pit for the septic tank is a foundational step in the installation process, setting the stage for the entire system. The pit's size must be carefully calculated to accommodate the septic tank, ensuring it has enough space to function effectively. However, this step isn't just about excavation. It also involves meticulous planning for the inlet pipe. The optimal diameter of 110 millimeters for the inlet pipe is essential to facilitate the proper flow of wastewater into the tank. A well-sized pit and the correctly sized inlet pipe together create the groundwork for a functional and efficient septic system. After the excavation is complete, the septic tank installation proceeds to the critical phase of lowering the tank into the prepared pit. Once the tank is in place, the next significant step involves filling it with liquid. To achieve this, the tank is gradually filled section by section. It is imperative to maintain a close eye on the level of liquid to prevent differences of more than 15 centimeters between sections, ensuring even distribution within the tank. The liquid used for filling must meet stringent cleanliness standards, as it will play a crucial role in the tank's subsequent function. The water level should be maintained at approximately 20 centimeters above the fill level, ensuring optimal functionality and capacity for wastewater treatment. To achieve this, a specialized cement mixture is meticulously prepared. This mixture is a key element in preventing the septic tank from deforming over time, which is essential for its long-term functionality. The specific proportions of the cement mixture are vital to its effectiveness, and these details are available in Multiplast's instructional videos, providing a comprehensive guide to achieving the correct consistency and strength. The installation of the inlet pipe is a crucial stage in the septic tank setup. The choice of the inlet pipe diameter depends on its expected length. For pipe lengths up to 15 meters, the optimal diameter is 110 millimeters. For lengths up to 20 meters, a 160 millimeter diameter is recommended. And for lengths up to 25 meters, a 200 millimeter diameter is ideal. It's important to note that 90-degree bends in the inlet pipe are highly undesirable. To avoid blockages, 2 45-degree bends, 3 30-degree bends, or 6 15-degree bends should be used, as smoother bends reduce the chances of effluent blockage. After installing the inlet pipe, specialists proceed to insulate the septic tank. Detailed information about the material and insulation methods can be found in Multiplast's other videos on their channel. During the final filling stage, it's important to remember that openings should never be below ground level. Burying the openings is prohibited because it could risk rainwater entering the septic tank and make servicing the tank challenging.
The cage welding machine is a specialized piece of equipment used in concrete pipe manufacturing. It welds together longitudinal and circumferential steel bars to form the structural steel cage. The cage welding machine is a specialized piece of equipment used in concrete pipe manufacturing. It automates the assembly of steel cages, which provide structural reinforcement to the pipes. This machine precisely welds together longitudinal and circumferential steel bars, ensuring the cage's strength and durability. Placing the steel cage into the mold is a crucial step in concrete pipe manufacturing. The mold, designed to match the pipe's dimensions, is positioned in a prepped hole. The steel cage is carefully centered within the mold, ensuring structural support and reinforcement for the concrete pipe's desired shape and strength. Concrete feeding into the mold is the process of filling the mold with a specialized concrete mix. The mix is carefully placed to achieve even distribution and prevent air pockets or voids. This step is essential for creating a concrete pipe with the required strength and durability. Concrete feeding and core vibration involves simultaneously adding concrete to the mold and applying vibration to ensure even distribution and prevent air bubbles. Pressing and fixing the mold is a critical step in concrete pipe manufacturing. The mold, filled with concrete, undergoes a pressing operation, which compacts the mix and eliminates voids. Fixing the mold securely in place during the initial curing phase maintains the desired shape and dimensions of the pipe. This process enhances the structural integrity and durability of the pipe, ensuring that it can withstand the external pressures and stresses it will encounter in its intended applications. Pressing and vibration in concrete pipe manufacturing further shape and consolidate the concrete. This process removes imperfections, increases structural integrity, and enhances the pipe's durability and strength. Removing the pressing head involves detaching the component used for shaping the concrete. Lifting out the mold from the hole is a delicate operation. After the concrete pipe has sufficiently cured, a lifting mechanism is employed to carefully extract the mold from its placement. Precision is paramount to prevent any damage to the freshly manufactured pipe. This step ensures that the concrete pipe remains intact and maintains its structural integrity. Once successfully lifted out of the hole, the pipe is ready for the final stages of inspection and quality control before it is put to use. Demolding is the process of carefully removing the concrete pipe from the metal mold once it has sufficiently cured. This step is critical to ensure that the pipe retains its shape and structural integrity. The mold is typically opened in a controlled manner, and the freshly manufactured concrete pipe is gently extracted, avoiding any damage. One significant advantage of this process is that the mold can be reused. After demolding, it is thoroughly inspected for wear and any necessary repairs. Once confirmed to be in good condition, the mold is prepared for reuse in subsequent concrete pipe manufacturing. This recycling of molds is not only environmentally friendly but also cost-effective, as it reduces the need for frequent mold replacements, saving resources and reducing production costs. It exemplifies the sustainable and efficient practices in the concrete pipe manufacturing industry.
The process initiates with a central control system managing pallet movement. This computerized control system coordinates the movement of pallets through various stations, ensuring a seamless workflow. Pallets, which act as the foundation for the concrete walls, undergo a thorough cleaning process. At this stage, precise measurements and design outlines are plotted onto the cleaned pallets. Shuttering station. Molds, precisely tailored to wall specifications, are secured to pallets, defining shape and structure for pouring concrete, ensuring accuracy and consistency in the final product. Release agent applied to molds to prevent concrete adherence during pouring. Steel cage fabrication involves precise assembly of reinforcement bars, according to wall design specifications. Skilled workers place and secure these cages within the molds before concrete pouring. The arrangement ensures structural strength, reinforcing the concrete against tension and compression forces. Proper installation, alignment, and securing of the steel cage are critical to the durability and integrity of the precast concrete walls. Concrete placement is a meticulous process involving skilled workers pouring the prepared concrete mixture into the molds. Careful attention is paid to ensure uniform distribution and eliminate air pockets, ensuring structural integrity. Vibrators may be used to assist in settling the concrete and removing air bubbles. Precise pouring techniques and consistency in mix ensure uniformity, strength, and the desired finish of the precast concrete walls. The curing chamber provides controlled conditions, regulating temperature, humidity, and time to facilitate optimal concrete curing. This controlled environment supports the chemical reactions within the concrete, enhancing its strength and durability. The carefully managed curing process helps prevent cracking, ensures uniform curing throughout the walls, and allows for the attainment of specified strength levels before the walls are moved to the stripping station. At the stripping station, the cured concrete walls are carefully removed from the molds. Skilled workers employ techniques to delicately detach the molds, ensuring the integrity of the concrete surface. This step demands precision to prevent any damage or imperfections to the finished walls. Once the molds are removed, the completed precast concrete walls are inspected for quality, surface finish, and adherence to design specifications before being prepared for transportation to construction sites. These cages, made of high-grade steel, are critical for providing the necessary structural support to the piles. Their production is fully automated, ensuring precision and consistency in every cage produced. Fully automated reinforced cage production involves advanced machinery intricately weaving high-grade steel bars according to precise specifications. Controlled by computer systems, this process ensures consistent and accurate assembly of the cages, optimizing structural integrity and minimizing human error in the production of precast concrete piles. Once the reinforced cages are completed, they transition seamlessly from storage to the molds. This transition is a pivotal step, requiring careful handling to ensure the integrity of the cages remains intact. Advanced machinery facilitates this transition, minimizing any risk of damage. Controlled concrete pouring is the subsequent step, where the molds are precisely filled with concrete. Following the pouring, the pile molds undergo meticulous finishing, where the surface is smoothened and any imperfections are addressed. The purpose-built curing chamber is a controlled environment designed specifically for curing precast reinforced concrete piles. It maintains optimal temperature, humidity, and ventilation conditions, crucial for the curing process. This specialized chamber accelerates concrete strength gain, enhancing durability and reducing the risk of surface defects. Its precision-controlled settings ensure uniform curing across all piles, guaranteeing their structural integrity and longevity in diverse construction applications. With up to 50,000 linear meters in stock, the facility ensures an ample supply of precast reinforced concrete piles, readily available to meet varying construction demands and project timelines. Finally, during installation, these precast piles are strategically positioned to serve as sturdy foundations, supporting structures with resilience and stability, making them integral components in various construction projects, from buildings to bridges.